Okay, so I'm going to talk about what exactly is a double integral. And what makes it, what's double about it, the fact that it's double, that's just 2D. The fact that it's an integral means it's somehow going to be similar to what we remember from single variable calculus, where you have two limits. This actually corresponds to an interval I. So you could actually write this thing as I. And so the integral, it's a very easy to understand definition in single variable calculus because it's just the area under f on the interval I. And it's actually the signed area, right? Because you could have f of x equals x. And so you take the integral, it's actually 0 because that's the signed area. So the double integral is really just the same thing. It's, if you have, let's just use a rectangle, for example, and I'll call this a region, not an interval. And let's just say you have, put a surface on top of it, like a sphere, like a hemisphere. Well, you can ask, what is the volume now enclosed by the surface over R? Like, this is actually just going to be the definition of the double integral. If this surface is given by f of x, y, then this volume will just be the definition of the double integral. And it's actually the signed volume. Because again, we could have surfaces which are negative. For example, you could just do f of x, y equal to x again. And if you go over here, that's just extending this thing in the y direction. Okay, so that's it. That's really all there is to these integrals. They're just volumes. But this is a geometric definition. And it doesn't actually help us get a number. And to that, we need math. Because math is the study of numbers. So that's how you get numbers. So mathematical definition it's very similar to singular variable calculus. So if you go back to 1D, it's actually just Riemann sums of rectangles because we know what the area is of a rectangle. And so that allows us to extrapolate the area for a non-rectangle. So just to draw this visually, what's going on, you partition AB, for example, into two line segments, and then you form rectangles based on the function height. And so this area is approximately the integral. And this thing, of course, is, well, it's space times height, right? So it's f of x1 times the width plus f of x2 times the width. And this delta x, of course, if you do even, it's just b minus a over 2. If you have even sides. So really, we're just going to do the same exact thing for 2D. So if we again partition the region, for example, let's just do a rectangle. So I'm now going to partition into 4 squares, 4 rectangles, and we can call this thing x11. We can call this thing x12. I'm just row comes before column. And then x21, x22, and I'm just going to write the same thing basically. So f of x11 delta a plus f of x12 delta a, f of x21 delta a, and you can guess what the last one will be. Here, of course, delta a is the area divided by 4. This, of course, b minus a, that's the length of the interval. So we could also call this a divided by n squared, because right, we have 2 in both directions, 2 subdivisions. So now you can see what it's like if you do 2 subdivisions. In general, mathematicians will like to generalize. They always like to write it down. So let's just do that here. If we have n subdivisions, I equals 1 to n, well, we'll have f of x I delta x. And then we'll do the same thing out here. This is I equals 1 to n, j equals 1 to n. And so then we just take one term, and then we stick it here. So f of, and then we change the subscripts. I, j, delta a. That's it. So that's the Riemann sum for n subdivisions. Oops, divisions. And of course, the delta a, it's this. Okay. So now the integrals will actually just be limits of these things. So if we send n to infinity, that gives you the integral. And you just change the delta to a d. And now if we send n to infinity here, now we get a double integral. It's you put the same integrand, except now we don't need, the ij goes to xy. And we're just going to put a dA here instead of a delta A. Okay, so the double integral is, again, just the limit of the Riemann sums as the subdivision gets large. Okay, and the nice thing about the mathematical definition is that the math, you can actually now convert this to an algorithm for a computer to evaluate. It's not a very good algorithm, the one that I just showed you, where you just choose the left-hand endpoints. Here you could do what I was doing was the middle point of these rectangles, but you can refine that. So I think that's all for this video.